All right, welcome back to the course. So we have found our best model. We fit the minimum samples leaf attribute using cross-validation, and we tested on the test set. Now let's look at the confusion matrix also on the test set. I'm using the exact same code we used from the logistic regression week, and the only difference is I'm of course, using the decision tree model. And so we see it's a little different. In fact, let's take a look at, well, first let's read this, and we're going to compare it to last week briefly, then just very briefly. Okay, so the model predicted 18 of the students in the test data would fail. It was right on 12, right? It was wrong on 6. 6 of those students actually passed. Now let's just look over at this is the confusion matrix in the from the logistic regression model on which we standardized the data, but we had not yet removed these students with the grade of 0. So these are an apples to apples model. So this decision tree, we haven't removed the students with the grades of 0. But here we have. So you can see there's definitely a difference, right? This logistic regression model only forecasted 12 students would fail. 9 of those it was correct on. But here we had more forecasts for failure, and it was correct on 12. So this model, even though the accuracy of its predictions of fail were less accurate, the recall is better. It actually identified more students that failed. We can see that in the classification report. And the last thing I wanted to show here is, I was just curious, honestly, and I wanted to just look at the predictions. So you can just visually, you can see if you compare this to the predictions from the logistic model, there's many more zeros here, which is our predictions for failure. And of course, there's 18 here and only 12 from the logistic regression. So it's a third more. All right, that's it. Of course, the reason I'm not, I've already introduced precision, recall, etc. So I'm not going through them again. There'll be some questions on this on the quiz. All right, great job, and I'll see you in the next video. All right, welcome back to the lecture. So one thing we want to talk about is, what if you use a threshold other than 0.5? So remember from talking about logistic regression, we could use the predict proba function to actually get the probabilities for the predicted probabilities for the two classes. So this first column is the predicted probabilities for failing, and the second is for passing. And if the probability is over 0.5, then that's the label you get. And these probabilities have to sum to 1. So if it's a 5% probability of failing, then it's a 95% passing. So using that 50% threshold, this would be a pass, and it is. If you see up here, it's a 1. The next would be a fail, and it is. It's a 0. And then the next two would also be passes. And that's what you have, pass, pass. And then you could go down and you could just look. Whichever one's over 50% would be a pass or a fail. But we don't have to use 50%. We could use 80%. So let's use that. Well, the top one's still a pass. Then this is a fail. Now these are fails, right? They used to be passes. Now they're fails. So what does that do? Well, in a well-calibrated model, if you use a higher threshold to identify a pass, then your precision for identifying passes should go up, right? You're using a higher threshold, so you should have less cases where you predict a pass and it's actually a fail. So you should have an increase in precision. Now your recall will go down. You are not, because the threshold is higher, right? You're not predicting as many students will pass. So of the students that really do pass, you will recall, or you'll detect less of them. So let's just pretend that in our data set, 50 of the students actually pass. With a threshold of 0.5, you might correctly label 40 of those. As you increase that threshold to 80%, you might only correctly label 10 of those. Now, you may be asking, how does a decision tree output probabilities? Well, it just looks at the probability of the classes, or sorry, the distribution of the classes in the leaves on the training data set. So here we had 65 samples, 40 are fails and 25 are passes. So that's going to be about 60% are fails. And at home you can follow along and do the math, but approximately 60% of these are fails, so 40 of 65. And so any testing data point that ends up in this leaf, we'd say it has about a 60% of failing and a 40% of passing. Oops. All right. So in the next lecture, we will actually produce some classification reports and confusion matrices for different thresholds.